This short webinar. My name is Ron Pelly and I am VP Commercial at Humanizing Autonomy. We are a software company based in London with a laser focus on human beings, and we have a novel approach to navigating in an urban mobility setting. We think that this is, in fact, we know that this is relevant to autonomous vehicles and human-driven vehicles. And Dominic Noy is going to tell you, and he's going to show you why it's such a great approach. Feel free to submit your questions as they come up using the Q&A button. We will try to answer as many of them as possible at the end of the presentation, and if we don't get round to them, we will answer them subsequently. And if you run out of time or you want to submit a question some other way, the domain is @humanizingautonomy.com, and you can send them to either me, that's Ron @humanizingautonomy.com, or Dominic, just exactly as you'd expect to spell it. I'm now going to hand over to Dominic. Thanks.
Okay. Thank you, Ron, for this brief introduction. So welcome to the webinar, everyone. Hope you're all having very productive CES week. So I'm Dominic. I'm the behavioral data scientist at Humanizing Autonomy, and mainly responsible for our behavior prediction models for pedestrians, cyclists, e-scooters, and other vulnerable road users. My background is experimental psychology, cognitive science, and statistics. And for over 8 years, more or less, I'm working in the scientific fields related to pedestrian behavior. And for some years now, I'm absolutely passionate about how we can leverage our expert knowledge in this field to build robust and interpretable machine learning models. And today, I'm going to illustrate where robustness and interpretability is essential when building autonomous vehicles and advanced driver assistance systems. So let me share my slides. So as you all know, driving can be challenging. The driver must make decisions about how to use the steering wheel and the accelerator to reach the desired destination as efficiently and smoothly as possible, while following traffic routes and avoiding collisions. And planning and decision making requires here an accurate prediction of the future position of objects. And this is particularly challenging when driving in pedestrian-dense urban environments, due to the huge amount of diverse pedestrian behaviors that could potentially lead to a crossing. And current autonomous vehicle systems struggle when driving in such environments. They are either extremely conservative, so that the driving experience suffers from frequent and abrupt deceleration, or the systems are built in an unsafe manner, as we had experienced with the Uber accident in 2018, where the safety systems were switched off due to too many false alarms. And there has also been a recent hype, absolutely reasonable, but a recent hype about end-to-end deep learning for pedestrian crossing prediction. And the problem is, while this approach is very powerful, certainly, we don't really understand. We don't really understand how decisions are made, nor can we obtain reliable and valid estimates of the prediction uncertainty. So how certain are their predictions? And therefore, the widely accepted industry standard for pedestrian crossing prediction is still to build simpler, more transparent, and interpretable models. And therefore, today, my goal is to show you that the current state-of-art industry standard doesn't go far enough, that we need to model the mind of the pedestrian. We need cognitive models to predict their crossing, and that we are able to do this at Humanizing Autonomy. So what is the state-of-art industry standard? Current autonomous vehicles and driver assistance systems are able to detect and localize static and moving objects, and they can distinguish between the different types of objects. And those systems are actually already pretty good in detecting and localizing pedestrians. And the information that those systems have about the pedestrians looks similar to what I'm going to show you now in a video. Just hang on. So you will see now a black box covering each pedestrian. And I'm going to present all the videos in this presentation, in this webinar, 6 times slower than the real than normal speeds, so that a bad Wi-Fi connection hopefully doesn't prevent you from seeing what I can see. So please focus, for example, this black box here, which is a pedestrian. So the black box represents what the system knows about the pedestrian, which is basically the pedestrian position over time. And now, based on the current and past position of the pedestrian, represented here as the black box, the future position of the pedestrian can be predicted. And based on the predicted positions to the future, it can be inferred if the pedestrian is going to cross in front of the vehicle. And the underlying models are often called state space models, dynamical systems, linear and nonlinear Kalman filters, extended Kalman filters, and so on. We call this the physics model, or the physics model approach, because it uses distances and their derivatives, velocities, accelerations, and sometimes map information of vehicle and pedestrian to predict crossing. And while the physics model approach has a long history in signal processing, navigation, and robotics, this approach has also its shortcomings, which I'm going to present you now in a couple of videos and a very quick quantitative evaluation. So the same video as before. So please focus now on the right corner again. And from behind this corner will appear a pedestrian. And you will see a red frame around the pedestrian, around any pedestrian, if the physics model predicts that the pedestrian is going to cross in front of the vehicle. And now you should see the red box. And so as you can see, the physics model falsely predicts crossing here. And this highlights that false alarms can occur when the pedestrian is approaching quickly and decelerates lately. And such behaviors are frequently observed when visibility is reduced by parked cars or corners with narrow sidewalks, as it's here the case. So let me show you another example. So please focus on the pedestrian coming from the left. And again, you will see a red frame around the pedestrian when the physics model predicts crossing. And here you can see now the pedestrian is detected. So a turning pedestrian is detected late by the physics model. So it's very common that a pedestrian walks parallel, close to the vehicle lane, and turns head and shoulders to verify if crossing is safe. And crossing will follow in such a situation if the pedestrian doesn't perceive any risk associated with the crossing. A physics model doesn't capture this and predicts crossing much later than a human driver would do. And let me show you another example. So please focus the two approaching women here from the left. And again, the red frame, and here you can see the red frame already, indicates that the physics model predicts crossing in front of the vehicle. And you will see that the physics model struggles with the second woman here with the red jacket. So still no prediction. So this is very common. The pedestrian approaches the vehicle lane, but before crossing, she decelerates or stops and monitors the behavior of the approaching vehicle to verify if crossing is safe. So by the way, now she's detected, now she's predicted to cross because she starts moving. So pedestrians in such a situation might cross when they're standing there, when they're approaching, they might cross depending on their awareness of the vehicle. Is the vehicle, for example, decelerating? The pedestrian driver communication, does the driver communicate to give way to the pedestrian? Are there other pedestrians already crossing? And is there a traffic jam so that the vehicle couldn't go further anyway? And there are more factors. Apparently such dynamics are hard to capture by a physics model approach. So let me go back to the slides. As you could see, the physics model struggles with quickly approaching pedestrians, although they are aware of the quickly approaching vehicle. Then turning pedestrians, standing or strolling pedestrians, and communicating pedestrians. So now let's turn to our behavior model. At Humanizing Autonomy, we merge statistics, machine learning, and psychology to build probabilistic machine learning models that, on the one hand, learn from data, but that are also guided by our prior knowledge. And based on our research and plenty of observational studies, we obtain prior information about the model structure and the relevant latent variables, the underlying distributions and their parameters, and the input features, the latent input features. Sorry, not the latent, the input features or variables. So for instance, we concluded that it's important to model those latent variables here, which is the vehicle awareness, the crossing risk perception, and the intention to cross the vehicle lane. And by the way, this is just an illustrative example. So our models look different, and we have more than those. We have more variables than those three. So we learned basically how to infer from the sequence of images, how to infer from the dash cam, how to infer those hidden or latent variables, how it's called in statistics or machine learning, or those psychological constructs, how you call it in psychology. And we also learned how to combine those to predict crossing. And so in the following, I show you the same and similar videos as before, but you're going to see the crossing prediction output of the behavior model now alongside the physics model output. So first I'm going to show you scenarios that can be observed very frequently. So this is the same video as before. You have seen it before. Please focus on the two women here on the left side. And the physics model crossing prediction is again displayed by a red frame, as you can see here, and around the pedestrian. And when the behavior model predicts that the pedestrian is going to cross in front of the vehicle, you can see a blue frame around the pedestrian. So both can be simultaneously there, apparently. And here you can see, so the behavior model already detected her. Here you can see that the physics model doesn't predict that this pedestrian is going to cross. And why? Because she's standing at this moment. But she's just a careful crosser. So she's verifying if crossing is safe. And you can't see it perfectly because we blurred the faces, but she's looking at us before she starts crossing. So the behavior model does a better job here and predicts correctly since start that she's going to cross. Now I show you another video. Please focus first on the two pedestrians approaching from the left, and then the two pedestrians approaching from the right. And again, the physics model is displayed in red and the behavior model is displayed in blue. And you will see, and you can see right now already, hopefully, that the physics model is struggling to predict crossing for those pedestrians, while the behavior model does, again, a pretty good job. And this is particularly at unmarked crossings, at slow speeds and pedestrian-dense environments. It's not always clear who will yield. Is it the driver or is it the pedestrian? And in such situations, you can usually observe an increased pedestrian-driver communication to disambiguate those situations, for example, through eye contact. And this often results in an active dialogue between the pedestrian and the vehicle to clarify who gives way, while keeping the interaction as smooth as possible. And if, for example, the driver isn't visible, this is usually through the acceleration and the deceleration profile. And this is called a negotiation about who will cross first. And for an IAV, it's crucial to understand such situations, to know if acceleration is appropriate, to communicate no yielding, or to decelerate to communicate yielding. And our behavior model can capture when ambiguity increases and a negotiation is about to start. So let me show you another example. Please focus the pedestrian who is standing here. And again, the behavior model is again blue and the physics model is red. And he will look at us. You can't see that perfectly. He looks at us and the vehicle decelerates and the behavior model already detected him, that he's going to cross, while the physics model is again delayed. So show another example. Here's, you can see a standing pedestrian. Please focus this pedestrian here. He will be occluded by this crossing pedestrian. And again, the physics model will be displayed in red and the behavior model in blue. And this pedestrian has a phone, so he's distracted. So this example shows that a standing pedestrian who's distracted follows another pedestrian, and this is captured by the behavior model, while the physics model again is delayed. Let me show you another example. So this is the example that you have seen at the beginning. Please focus on the pedestrian coming from the left. And the behavior model is blue and the physics model is red, as all the time. And you can see already that the behavior model captures much earlier the turn in pedestrian than the physics model. So now she's captured by the physics model. And very importantly, all of those examples aren't edge cases. They happen all the time. So they should suggest that for accelerating and decelerating efficiently and smoothly, you need a more profound understanding of the pedestrian than what the physics model can actually offer. And now I'm going to show you examples of scenarios that happen less frequently, but false crossing predictions would result in severe unwanted consequences. So please focus the pedestrian coming here from the left side with a black jacket. And again, because of the blurred face, you won't see that he looks at us, but he's looking at us for a very long time. And again, the behavior model is displayed in blue if it predicts that the pedestrian is going to cross, and the physics model is displayed in red. And please track him. So he's quickly approaching the curb, but he's aware of the approaching vehicle. And while the physics model wrongly predicts crossing, the behavior model doesn't predict so. So you couldn't see any blue frame around the pedestrian because the behavior model was predicting correctly that the pedestrian wouldn't cross. Let me show you another example. So please focus now the pedestrian coming here from the left side behind the corner. And again, the behavior model is blue and the physics model is red. And you will see right now there's a red frame, and you will see that so a similar situation occurs. The physics model in red falsely predicts crossing, although the pedestrian is aware of the quickly approaching vehicle. Let me show you another example. Please focus the pedestrian coming from the left. And again, he looks at us. And you can see the same pattern. A wrong crossing prediction of the physics model in red. And I could show you here many more of those examples, but I think that you got the point now. And then I show you a final one. So please focus this is again a video I've shown at the start. So please focus this corner here. And you will see the same pattern. A wrong physics model crossing prediction red and a correct behavior model prediction blue. So the last four examples, for the last four examples, the physics model was falsely predicting crossing, which if using such situations for decision making would result in emergency braking. And here in the video, you might have noticed that the driver didn't brake or decelerate at all. I know it's a bit hard to spot because of the slow motion, but there is no significant change in velocity of the vehicle. And why is that so? So the driver has a cognitive model of the pedestrian. And the driver knows about the intention to cross, the pedestrian's intention to cross, yes. But the driver also knows that the pedestrian knows that crossing in front of the vehicle isn't a very good idea in such a situation. And so in all those examples, you could observe an interaction between the pedestrian and the driver. And for ensuring a smooth interaction, both agents require such a cognitive model of the interaction partner to anticipate their actions and respond appropriately. And in contrast to the physics model, our behavior model captures this because it combines different dynamic variables like the vehicle awareness, the pedestrian's perception of risk associated with the crossing, and the intention to cross. And it combines them all in a cognitive/machine learning model. So also, because we built the behavior model in a modular manner within the Bayesian framework, it can be easily combined with other models. So this approach is interpretable so that we understand the limitations of our model and when it's uncertain, so very important. And because it is smaller and fast, predictions can be done on simpler devices in real time. And in addition, it's applicable to different contexts and environments. So importantly, so those are advantages that the physics model also has, but the physics model is not flexible enough. And those factors are all limitations of, for example, a deep learning approach. So we combine the best of both worlds somehow by making those additional assumptions about how the cognitive models, how the model looks like. And we backed this up with a quantitative analysis showing that we can predict up to 4 seconds in advance, and 4 seconds is a lot, where the pedestrian is going to cross. Of course, it depends on the situation, but and the behavior model reduces the prediction error of the physics model by more than 50%. So, concluding, I hope I could convince you that we got some evidence here that behavior machine learning models can mitigate the limitations of the physics model-based approach by having a more profound knowledge of the pedestrian. And by capturing complex vehicle-pedestrian interaction dynamics, the behavior model can be used when combined with further physics to make decisions about acceleration, deceleration, and emergency braking or other means of communication. And we claim that only a profound understanding of the psychology of the pedestrian can enable a safe and smooth ride through downtown. So thank you very much for listening. I hope there are some interesting questions, and hand over to Ron.
Thanks, Dominic. Yeah, so there were, I think we have 3 questions so far. One of them, I'm not sure, is to do with the difference between a physics model and a behavioral model, but I'm going to read it in any case. And I'm even going to try to answer it, but you may correct me. It says, why are the pedestrians that are conducting a crossing not recognized, therefore no bounding box during the end of their crossing? Is this intentional? So my answer to that, you may consider this, Dominic, but my answer to that is that that's just because we're really interested in their intention and when they're about to cross rather than afterwards. And in fact, what you're seeing is to do with detection rather than any difference between physics and behavioral models. Perhaps I didn't answer that perfectly correctly, so I'll give you a chance to add to it.
Yeah, if I understood it correctly, so if I understood the question correctly, I think you're asking why the boxes only appear when we predict crossing, right? So yeah. So we didn't display. So we detect all the pedestrians there. We didn't display the detection. We didn't display the bounding box when we detect the pedestrian. We just display the bounding box when we predict that the pedestrians are going to cross in front of the vehicle. I think.
Gotcha. Okay. Well, that's yeah. So that's actually kind of what I was trying to drive at, which is we're interested in the start of the process and predicting what's going to happen rather than what has already happened and that somebody's just crossing. I hope that's a good answer for you. And I've got 2 other questions here. One says, could you explain interpretable and why that's important?
Right. So let's say, I mean, interpretability is a huge concept, and I could talk about it for 30 minutes. But I'd say interpretability usually means that we as a human or as a researcher can understand the decision making of the model. This stays in contrast with, for example, deep learning, where you have up to billions of parameters and billions of connections between the different latent variables, the different nodes in the model. You can't really understand how the decision making is done. And it's also difficult to obtain uncertainty because those models are so huge that you can't just use a Bayesian approach. So in contrast, if you have a lot of prior knowledge and you can constrain how the model has to look like, you can use much fewer parameters. Mm-hmm. And if you do that, you start understanding, and you can start understanding. So you can construct basically meaningful relations between the different variables in your model. And by this, you obtain a big understanding. If I have time, can I talk a bit more about that one? Or are there many more questions?
No. There's one more at the moment, but go ahead. I think it might be useful for the audience.
Okay, all right. So I think that when you have deep learning models, what you a lot of times do, you try to explain them by different visualization techniques or by building smaller explainable models that explain the output of the deep learning model. But that is, in the end of the day, isn't used because they are only approximations and their accuracy are usually worse than the deep learning model. What we do is we build, where we can, interpretable models in the first place. And we can do this because we really study what's the problem, what are the input features that go into the model, how the variables are related to each other. So we try to understand the problem really well instead of throwing a lot of data into the to the model and hope that the machine learning algorithm just learns the right relations. We try to feature engineer a lot, but by basically guided by the behavioral studies we conduct. So that we have a lot of understanding about when biases might occur, and when those models might fail, and therefore the development cycle to improve such models is much quicker. Plus, we can make it fully Bayesian, so we have a very reliable and valid estimate of uncertainty. I think that's enough, right?
Yeah, I think so. And actually, there's the next question is related to that, actually, because you talked about being able to do things rather quickly. So, or I think that's more or less what you were saying. But the other question was about how you adapt models for different cultural settings.
Right, that's of course a good question, and that's what humanizing autonomy stands for. So first of all, we test a lot of our models in London. London is extremely diverse, multicultural, and if you're able to predict reliably and well, if you are able to predict really well pedestrian behavior in London, you probably can, you can do it in other European cities. And we had, I had an interesting case where I get data from Munich, and I found it so easy to actually predict what the pedestrians are going to do because the behavior here in London is so much more diverse. But that's just a side note, actually. More importantly, we do, so when we get data from a different city or from a different country, we do our behavioral analysis. So we have our hypothesis, how the behavior is caused, and we look if our model fits to our model that we have trained on earlier data, if it fits to the new environment, and where are the limitations of this model. So we do this model checking all the time when we get new data from different contexts. Plus, we usually fine-tune then and train context-specific with context-specific data.
Does the interpretable nature of what we're doing, does that make it easier to adapt to those new cultural inputs?
Definitely, because the interpretability also a lot of times implies that those models are decomposable in different subcomponents. And for example, to give you an example, intention to cross and risk perception. And the intention to cross might look similar across cultures, so it doesn't change as much as the risk perception. So therefore, you just have to fine-tune, or you just have to correct the bias in one of those components and not in the entire model. So it certainly helps a lot that when you have interpretable models and you bring them to new cultures, you understand usually very quickly their limitations and can correct them at a specific place where they think where they're not correct. Yeah.
So Dominic,
by the way.
Yeah, I think we all decided that we wanted to try to curtail this at this moment after 30 minutes. So thanks everybody. If your question did not get answered, it will get answered subsequently, and we'll send an answer via email. Thank you very much for attending. And I hope that this was enjoyable. Remember, if you have other questions, feel free to send them to us via email, either to Dominic or Ron at humanizingautonomy.com. Thanks very much, everybody. Bye.
Thank you. Bye.